So we have seen so far how to calculate the error vector magnitude, what this means, and now we're going to look into the Agilent vector signal analysis software to see how we can use it to analyze our higher order modulation formats. So last time in the homework we looked at binary modulation. Now we're going to be looking at APSK and 64 QAM. So going on, we can see the homework assignment 1, how we, so this is homework assignment 1, we had a part in MATLAB and we had a part in the VSA Agilent software. Once again, MATLAB will play the role of the transmitter and the channel, and the VSA plays the role of the receiver. But of course, this VSA software mimics a real-time oscilloscope, and it is not aware of the bits sent. So this is not a bit error rate tester. It's simply a sophisticated oscilloscope. So it cannot measure the bit error rate, and instead it will be looking at the error vector magnitude. So one difference between the homework assignment 1 and the current one is you can see here in blue I've highlighted what was generated in MATLAB in the first homework assignment. And we can see that there was an RRC, a root raised cosine filter, for the transmitter. There's the channel, which adds additive white Gaussian noise. And then, of course, at the receiver, we'd have the match filter. And in the case of the homework assignment 1, that was included in MATLAB. Now, as we go to homework assignment 2, the difference between what is done in MATLAB and what is done in the VSA software, where the VSA software just looked after the match filter in the case of homework 1, it will be a little different in homework 2. So this is for homework 2, and we can see that the root raised cosine filter is now in the VSA. And so we have to tell the VSA that we are doing a root raised cosine filtering, and we have to tell it the roll-off that we're using. And it's important that it has this information because it aids it in the calculation of the error vector magnitude. For the calculation of error vector magnitude, we have to have some idea of where the true transmitted symbol would be, and knowing about what filter was used to transmit it helps in making a better estimate. So in the simulator, you will be using MATLAB to generate, again, signals which will be input to the VSA software, and we'll be doing both 8PSK and 64 QAM, for different signal-to-noise ratios. So they will be generated in MATLAB, and in fact, the signal-to-noise ratio will be 40, 30, and 20 dB that you'll be examining. So there'll be 2 modulation formats, 3 SNRs, so 6 different data files that will have to be generated. We're going to use a roll-off of 0.5 for our filtering. So now we come into the part about what you will be reporting. So inside of the VSA software, there will be some calculations being made, and we'd like to compare them with what we know to be the ground truth. So because the signals are actually being generated in MATLAB, we can control them completely. So for instance, we know exactly what the signal-to-noise ratio is, 40, 30, and 20, the case being. So there is a way to calculate the correspondence between the signal-to-noise ratio and EB over N0. There'll be a capsule that goes into the derivation of this, which we haven't seen yet, but for the homework assignment, it's okay, you don't need it. You just need to know what the theoretical spectral efficiency is, because the relationship is just that the signal-to-noise ratio that we have calculated in MATLAB is equal to the ratio EB over N0 times the spectral efficiency. And of course, here's 8PSK, and for PSK, the spectral efficiency we saw was log 2M. So if we know these numbers, it's very easy to calculate EB over N0. And I'd like you to just fill in the column here, making this calculation to see what EB over N0 is according to MATLAB. So in the next 2 columns, we'll be recording measurements made by the vector signal analysis software. And in the first case, we'll be recording the error vector magnitude, and the units of the error vector magnitude will be the percentage, root mean squared percentage. And then the VSA software will also supply you with an SNR. And just so you know, this SNR that it's going to be reporting is going to be calculated per this relationship that we just saw in the development of the error vector magnitude. So you'll be reading these numbers right out of the VSA software and recording them in this table. Now, the two remaining columns are calculations that you will be making. And the column that says BER EVM is going to be using a theoretical equation for the bit error rate that you will be applying, assuming that this signal to noise ratio is true. And the theoretical bit error rate, you will be comparing it to, well, you'll be putting into this column, will be calculated by using the EB over N0 that we have from MATLAB. Now, what's tricky is you saw that we did this conversion from signal to noise ratio to EB over N0 for these two columns. Now here I'm asking you to calculate the bit error rate based on the EVM estimate of the signal to noise ratio, but that means you're going to have to do a conversion from SNR to EB over N0 for this measured value of SNR. So here is the equation for the theoretical bit error rate. And the theoretical here, I mean that you plug into the bit error rate equation, the EB over N0, which one? The one in this column. Now, when I go here, and what I want you to fill in this column is where we're using an EB over N0 from the VSA software. I don't actually have a column here for that. I just have a column for signal to noise ratio. And that's because I want you to think a little bit about how you would do that conversion. So what do we get for this? How are we going to use the conversion? That's one of the choices that you're going to have to make and perhaps justify. Certainly we know already that it should be that the EB over N0 is just the signal to noise ratio divided by the efficiency. The question is, what is the efficiency, the spectral efficiency? So we know here we're using the theoretical value for the spectral efficiency. If I go back, here I said that when you're calculating in this column to just use this theoretical. And the question is that what you should also use to do the conversion here? Should you also use this spectral efficiency, or should you use a spectral efficiency which is calculated inside the VSA software? So there is a different spectral efficiency, and it's not the spectral efficiency which is coming from theory, but instead it is simply the bit rate divided by the occupied bandwidth. And you can measure the occupied bandwidth with the VSA software. So you take the raw definition of spectral efficiency, R, the bit rate, divided by the occupied bandwidth in hertz, and you get bits per second per hertz. And you could use that to calculate this. And of course, depending on which one you use, you'll have a different EB over N0 and you'll get a different bit error rate. So in order to be able to make this choice, what is the spectral efficiency from the VSA, you'll be doing a measurement of the spectral efficiency in VSA. So now I have you sort of spell out what you want to do here for these two values. So in the case of theoretical, here you'll be doing the log to m, and in the other one you'll be using the one you measure. Give you two different EB over N0s that you can use in the calculation of the bit error rate, and you'll see which one is more accurate. Okay, so inside of the VSA software, we'll be having to first generate the file of MATLAB. And of course, that will generate a .txt file, which you'll be uploading. So we'll go, as we did in the first homework, you go to File, you'll do recall setup. You'll start with the setup file, number 2, that I'll have on the web page for you. And then you'll do the recall recording, which will be the text file that you create in MATLAB. And of course, there'll be 6 cases. 3 SNRs for APSK and 3 SNRs for 64 QAM. Then we're going to go into measurement setup, where we're going to tell it what the modulation format is for the file that you'll be sending. So you can see here in format, we have 16 QAM. If you do the drop down here, you'll be able to choose 8 PSK, and you'll be able to choose 64 QAM. So again, in this section, we'll be saying either 8 PSK or 64 QAM. In here, we'll give you the symbol rate, which you can calculate from this and get the 200 hertz. And the number of samples per symbol is 20 in this MATLAB file that's being generated. In this section, we'll be setting the values for the filter in the VSA software. And if you recall, we were going to use root raised cosine filtering with a roll-off factor of 0.5. So in the VSA software, the first setting we have here is RX filter, and this is the receive filter and what the VSA software will apply to the uploaded signal before it does all the visualization. And so that's the receiver filter. And then it has to generate a reference point for the constellation, so what the nominal centers of the constellations are. And for that, it needs to have the total filter. And of course, the total filter is a raised cosine, because we would have had a root raised cosine at the transmitter and a root raised cosine at the receiver. And then finally, the last point is the roll-off factor, which for this exercise is 0.5. So the graphics that I'm going to ask you to submit are a couple of graphics. First one's called normalized constellation. And you can see here is an example of it where you see the circles where the concentrations are for the received data bits. And then you can also ask for the reference underlying the reference constellation, which is the dot at the center. So here we have all of the points. They're normalized on the nominal transmitted ones, but we can't really see them because they're superimposed on top of the reference one. But if you click on this, you will undo the overlay. You'll turn off the overlay, and then we'll just see the reference constellation underneath. So I'd like you just to do that so you understand what's going on inside of the software. So you'll see what the reference is that it's using, and, then you'll see the actual received symbols. I asked that you report the EVM, and so if we look now, it says the 16 QAM, this is 16 QAM example symbols / errors. This is a table where a lot of information about the received and detected signal is being reported. And in particular, you'll see the % RMS, EVM, and be careful, sometimes it's milli percentages. And then finally, there'll also be an estimate of the SNR in dB. So these are the two values that you're going to be entering into your table. You'll also be asked to record the occupied bandwidth in order to be able to calculate the spectral efficiency. And for that, be careful which spectrum trace you look at, because one of them will tell you that you cannot use the occupied bandwidth, OBW, to calculate automatically what the bandwidth occupied is. So if you go and use just the channel spectrum, that will work. But if you do this saying measured spectrum, that will not work. There's two different operations. So be a little careful of that. But once you do have the right display of the spectrum, the power spectral density, you will be able to use the OBW command just as you did in the first homework assignment and ask for the 99.5% occupied bandwidth. And then you have the bit rate, which you can calculate based on the symbol time, which is given here, 5 × 10⁻³ and the number of bits per symbol. So it'll be different for 8 PSK and for 16 QAM. Okay, so that is the part that has to do with the VSA software and what you're supposed to be looking at for that section. So then we go on to the final section of the homework, which is sort of another departure. And in this case, what you're going to do is be estimating the so now we go on to the final section of the homework. We're sort of shifting gears. We did what was basically virtual experiment using the vector signal analysis software. And now we're going to go into a simulation of the performance, the bit error rate. So we have the bit error rate theory, what it should be. Now we have some experiment, what we were estimating based on the measurements we make on the error vector magnitude. And now in the last homework assignment, we're estimating it based on a Monte Carlo simulation, as if we did not know an equation for the bit error rate. And what we had to actually do is just send a bunch of bits, count how many times we made errors, and use that as an estimate of the bit error rate. So let me go into now the Monte Carlo simulation portion. So when I do a simulation that is called Monte Carlo or MC, I'm going to have in MATLAB the complete communications chain. So I start out by sending a bit. I have a sequence of bits I'm going to send, and I have a mathematical operations which model the transmitter. I'm going to add random noise, in this case additive white Gaussian noise. I could put it through a channel. In our case, it's going to be just an all-pass channel. And we're going to have a receiver. And the receiver is going to generate a test statistic. And the test statistic is going to go through some decision rule. I'll compare it with the threshold. And then I will be deciding what bit was sent. So I can model each one of these components as being entirely ideal, in which case I should get results that are just like the theoretical curve, should match theory. But if I wanted to know what happens with a non-ideal component, that's where Monte Carlo is terrific, because I don't have an equation. And so this is a way of simulating it. But for our purposes, we're just going to be validating that this is a good simulator, because I should get the same answer as I would for the theory, because everything is ideal in the MATLAB simulator that we're going to use. So the idea is we send a bunch of bits, we know what they are, we're in a simulator, and then we look at the decision that was made, and we said, is there an error or not? Was B equal to the estimated B hat? And if it's not right, I count. I count how many errors were made. So I send n bits, I count E errors, and then I make an estimate that the bit error rate, it's a frequency estimate, that it's E errors divided by n bits. And so what we're going to play with are how big these numbers n and E are to see what makes a good estimate of the bit error rate. So we can imagine that if the bit error rate is very small, I'm only making errors every 10 to the minus 6, 1 in a million bits. That means that I've got to have a whole lot of bits before I'll count any errors. So clearly this is going to depend on what the value of the bit error rate is, how large we have to make n. Now, if E is very small, if I'm not counting many errors, then my estimate is not going to be accurate, because errors, it's a probabilistic. So this is a frequency. I'm only estimating it. So if I count a whole lot of errors, well, then I know that my estimate is pretty good. But if I've only counted one error, well, did I get unlucky and the error came early, or was I very lucky and the error came later than it normally should? So if the error count is small, the estimate is not very good. Now, if n is very large, if I count a whole lot, well, then the simulation is slow. So it's not like I can just say, go for 1 billion bits, because that will slow down my simulator. Also, if I just say, I'm not going to stop, I'm just going to keep going until I count like 1,000 errors. Well, if E is too big, then really I'm getting a lot of precision, but maybe unnecessary, making my simulator slow unnecessarily. So these are the trade-offs I'd like you to sort of get a feel for in this homework assignment. So there is this BERT tool that we used to plot theoretical curves of the bit error rate. That was the first tab in the bit error rate. But there is a second tab which actually assists you in the Monte Carlo simulation. So you write your program to do the Monte Carlo simulation, but then this tab allows you to plot it and to plot it with the theoretical curves and to see if there's divergence or if it's the same. It just lets you sweep through the signal to noise ratio and plot your bit error rate according to that. And that's what you'll be doing in the homework assignment. So I'm going to be providing you with the code for these ideal components. And this is the code. It comes from a demo in MATLAB. And we can see that it uses these modulator and demodulator commands. So there's a QAM modulator and a QAM demodulator. And there's a command to add additive white Gaussian noise. There's a command that lets you count errors. So it's very automated. And we can see here that we have a conversion again from EB over N0 to SNR because the additive white Gaussian noise is keyed to SNR, but the bit error rate is keyed to EB over N0. So it's important to be able to convert between them. And you can see here for QAM modulation, we have this log2M. So after we've established the communications channels, we've said which M it is. M here is going to indicate how many points in the constellation. We come down here and we generate a message. And so this N here is telling us how many symbols I should generate. And of course, I'm going to be having random symbols between 0 and n minus 1. So then I actually send this message through my modulator. So I turn a sequence of symbols into points in the constellation. And I normalize the power, and then I send it through the channel. And the channel is, like I said, just an all-pass additive white Gaussian noise channel. Then after I've received it, I demodulate it. I take the points as they've diverged a little from the transmitted ones because of noise, and I demodulate them, make a decision, and then I count errors. And you can see here I'm counting the symbol error rate, and then I make a conversion to bit error rate. And we'll be talking about that a little later. But for now, you can just use these commands and not worry about this distinction between signal to noise ratio, symbol error rate and bit error rate. I'll be talking about that at the end of the week. So, of course, I said you're going to do PSK as well as QAM. And so there's a simple small change to go from QAM to PSK, but the rest remains unchanged. So what I ask you to do is to examine, I believe it's 18, these numbers may, this is the number, M equals 64. And for instance, here are some possible values that you will get. But the important thing is that I only ask you to look at one signal to noise ratio for this part of the exercise, and I just have you play with this number N. Suppose I only have 100 symbols that I transmit. Well, then I'll measure 0-bit errors. Suppose I make it bigger to 1,000, 0 errors. So is the bit error rate really 0? No, I just haven't had a long enough N. And for instance, when I get to 100,000, then I start getting, I count 12 errors, and then I get a certain estimate of the bit error rate. And by the time I go to 1,000,000 symbols which are transmitted, I'm counting 92 errors. And you can see the bit error rate estimate changes. And the higher the number of counted errors, the more accurate the bit error rate will be. And so this is to give you a feel for why we have to vary that. So after you've done it for one point of EB over N0, now we're going to do it for a whole range of points. And in this case, like I said, this was the theoretical tab where we would plot the theoretical curve, and you can start by doing that. And then there's also a tab which says Monte Carlo, and that's what we'll be looking at now. So again, in Monte Carlo, you're going to tell it what range you want to go, and in this example, it goes from 0 dB to 12 dB by a step of 3 dB, and in the homework assignment, I tell you the range I want you to look at. You could use a Simulink or a MATLAB model. You'll be creating a MATLAB file, and so you'll be telling it what is the name of your file. This is MDL, but you'll be doing a .m. It could be either one. And then inside of your program, you're going to have something that says the bit error rate. And I believe here it's BER. And so you would tell it, well, it's the variable called BER that has the bit error rate in it. And now here is the important thing. It's the simulation limits that we'll be looking at. So first it's the range. Then this down here is we're going to be telling it the maximum number of errors. Remember I said if you count too many errors, you're just having too much resolution and it's not useful. So putting something like 100 is a good idea. Any more than 100 is probably more than necessary. So this tab sort of manages for you seeing how many you've calculated. And I'll talk about that again in a little bit. And then finally, we have the maximum number of bits. This is like a stopping criteria, because if you don't put this in, if you're not sure of what the bit error rate is going to be, it could be extremely low. I mean, you could later find out that in theory it's 10 to the minus 10, and you could wait a very long time for MATLAB to measure that. It will never measure it, so you'll freeze up. So we have to give it a maximum number of bits, and that's sort of determined by how patient you are. So again, the file name goes here, and you'll be doing a .m file and the name with the variable. Now, in order to use this tab in the BERT tools, you have to follow a certain template, and this is the template that you would use. And you can see it says insert your code here. So the previous part is where we look at QAM, 8 PSK or 16 QAM, and then you'll be part of your assignment is just being able to put it into this template and use it correctly. And you'll have to break it into two pieces, and I'll let you figure out how it should be broken up between, you know, when you're setting things up and when you're actually counting. And so this is important because you're breaking it up so that you can let it manage how it runs a simulator to be able to stop at the maximum number of errors and to stop at the maximum number of bits. So basically, you're going to be doing sort of like batch processing. Maybe you'll do 10,000 at a time and then see, have I counted enough errors? No. So then you'll do another 10,000 and you'll keep going until you get to the right number of errors. So that's part of the assignment, is to sort out how this template works. And here, you can see that there's a part of the code provided which is establishing the system, and another part that's actually generating the data. So you can imagine that you can, of course you have to sweep the SNR, and I'll let you figure out where that should be. But this is the way you should think about how you would be dividing up the code. Again, this was from a previous one. It's 16, but I believe your homework assignment will be for 64 QAM. So in part 2, I'm going to have a discussion section, and the discussion is, you know, how good is EVM at predicting bit error rate? And you're going to look at these different estimates of spectral efficiency, and are they affecting how well EVM can predict bit error rate? And so it gives you something to think about and discuss for the homework. And finally, in part 3, I really want you to discuss is, you know, the number of errors, and to see for yourself, you know, how well you could play with the maximum number of errors, for instance, and see the impact on the bit error rate. Thank you.